Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus tollens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we introduced the rules of inference and deduction and explained how the validity of these rules relates to logical implication. In particular, we discussed the classic rule of modus ponens, which is fundamental to logical reasoning. In this session, we introduce several general rules, all of which are, in principle, derived from modus ponens. We invite the reader to verify that the conditional compound proposition corresponding to each rule is indeed a tautology, thereby confirming the rule's validity. We begin with the modus tollens, which reads, from if P then Q and not Q, derive not P. For example, if Chewy is sleeping, then Chewy is on the roof. Chewy is not on the roof. Therefore, Chewy is not sleeping. The next two rules concern conjunction and disjunction and are quite intuitive. The first rule is often called addition, which reads, from P, derive P or Q. For example, the following argument is valid. Chewy is sleeping. Therefore, Chewy is sleeping or Mochi is eating. The second rule is often called simplification, which reads, from P and Q, derive P. For example, Chewy is sleeping and Mochi is eating. Therefore, Chewy is sleeping. Trivial as they seem to be, these rules appear everywhere in mathematical writing. For instance, recall that a bijective function is one that is both injective and surjective. A monotonic function is one that is either monotonically increasing or monotonically decreasing. As a result, when we say the function is bijective, therefore it is injective, we are using the rule of simplification. On the other hand, when we say the function is monotonically increasing, therefore it is a monotonic function, we are applying the rule of addition. The next rule is called hypothetical syllogism, which reads, from if P then Q and if Q then R, derive if P then R. Here is an example. If Chewy jumps on the table, then Mochi jumps on the table. If Mochi jumps on the table, then Mochi breaks the bottle. Therefore, if Chewy jumps on the table, then Mochi breaks the bottle. This rule is useful in extending our chain of reasoning and allows us to move further in deduction. The disjunctive syllogism is another frequently encountered rule in deductive reasoning. It reads, from P or Q and not P, derive Q. For example, consider the following argument. Chewy has broken the bottle, or Mochi has broken the bottle. Chewy did not break the bottle. Therefore, Mochi broke the bottle. This type of reasoning is especially useful when a situation involves multiple possibilities. Just like a detective who has narrowed down a list of suspects, one can then eliminate options one by one until the correct conclusion is reached. Last but not least, we discuss reductio ad absurdum. Some authors may use this term interchangeably with the more commonly known proof by contradiction. Strictly speaking, the two are not exactly the same, although within the scope of our discussion, the distinction does not make a practical difference. The rule reads, from if P, then a contradiction, derive not P. For example, consider the following argument. If Chewy is sleeping, then Chewy is on the balcony. If Chewy is sleeping, then Chewy is not on the balcony. Therefore, Chewy is not sleeping. In practice, suppose we want to prove that a proposition P is true. To this end, we may assume that not P is true. From that assumption, we attempt to derive a contradiction. If a contradiction is reached, we can conclude that our assumption was false, and therefore P must be true. Many well-known results, such as the irrationality of square root 2 and the infinitude of prime numbers, can be proved using this approach. So far, the rules of inference we discussed have been essentially rules of implication. That is, they operate in one direction, and their validity relies on logical implication. In the next session, we will turn to rules of replacement, which can be viewed as valid rules of implication in both directions and are naturally related to logical equivalence.
信了，ten say。